All right, guys, welcome to lesson 5.2. So we're going to introduce you guys to a really important concept today called the extreme value theorem. So we'll talk about what the extreme value theorem is and when you're allowed to use it, and then how do you use this thing called the candidates test to find what the absolute min and absolute max of a function is. Okay, so last class we talked about, what is an absolute min, what is an absolute max, what is a relative min, what is a relative max. Well, today's lesson is going to focus on how do you find absolute extrema using the extreme value theorem and the candidates test. Now, in classes that follow, we're going to talk about how you can find relative extrema using a different kind of test. But today we're just focusing on how can you find the absolute mins and maxes using the candidates test and the EVT. All right, so let's go ahead and jump in here. What is the extreme value theorem? Here it is. It says if a function's continuous on a closed interval from A to B, then somewhere it has to have a highest point and a lowest point. The big trick here is that it actually needs to be continuous. Okay, if it's not continuous, the EVT doesn't work anymore. And since it's on a closed interval, those endpoints have to have closed dots. Your endpoints cannot have open dots on them. Okay, so for instance, it doesn't matter what kind of a graph you want to draw, so long as it's continuous with no holes, gaps, or jumps, and the endpoints are solid points, there has to be an absolute max and there has to be an absolute min. That's what we call the extreme value theorem. But as soon as you start putting holes, gaps, or jumps in there, it doesn't work anymore. So for instance, if we had this, and I told you this was an open dot here, well, we just lost it because since there's an open dot, it's not continuous. In last class, we saw that means there's also no absolute max at that point, which is where it would have been. Okay, or if your endpoints are not included, like if I drew this graph and I had this, well, once again, we blew it because it's not a closed interval. The endpoints are not open. They're not closed, and therefore we also lose it that way. So it has to be a continuous graph with no holes, gaps, or jumps, and the endpoints have to be solid dots. If that's the case, then there absolutely has to be an absolute max and an absolute min on that interval. So now that brings us to the next question. Okay, so the extreme value theorem just promises us that somewhere there is a minimum or a maximum, an absolute min and max, but it doesn't really tell us where that minimum and maximum is. So where do we look for it? Well, it has to be at one of two places. It's either going to be at the endpoints or it's going to be at a relative extrema. So if I'm looking at this graph right here, it's going to have, we know that the absolute min or the absolute max has to either happen at one of these endpoints or it has to happen anywhere there's a relative extrema. So basically on this graph, I have three places I need to look to see if there's an absolute max. And it turns out that yes, this one here is my absolute max. So in this case, the right-handed endpoint is my absolute max, and this relative minimum right here is my absolute minimum, and this one is nothing. So the EVT, the extreme value theorem, tells us that there is an absolute min or a max, but it doesn't tell us where. But the good news is we know where to look anyway. We either are going to look at the endpoints or we're going to look at the relative extrema, and that is where the absolute min or max would have to be located. All right, and that brings us to the big question then. How do we find the absolute min and max? We're going to do something called the candidates test. I like the name of this test because it kind of tells you what it is. What is a candidate? You guys know what a presidential candidate is, right? That's somebody who's running for president, someone who is a potential next president, right? Well, a candidates test tells us what are some potential options for the absolute min and the absolute max. And we already know who our candidates are. Our candidates are the endpoints, and our candidates are the relative extrema. Those are the candidates for where the absolute min or the absolute max is located. So we need to know how to find our candidates. So first of all, we want to make sure, that the extreme value theorem actually even applies to our function. Remember, the extreme value theorem guarantees us that there is an absolute min and an absolute max. Okay? We don't want to be looking for something that doesn't exist. So the first thing we want to do is make sure that this function actually has a min and max by making sure it satisfies the requirements for the extreme value theorem. In other words, we need to make sure that it's continuous. It should have no holes, gaps, or jumps. Okay? And in that case, it's going to be really helpful to go back to that little continuity of common functions worksheet that I gave you guys way back in Unit 3. We'll pull it up again in a moment. But for now, you need to make sure that your function has no holes, gaps, or jumps on it. Next, we want to make sure that we're looking at a closed interval. You need to make sure your endpoints are included. Now, just so you guys know, just because a function fails to meet the requirements of the EVT, that doesn't mean that there are no absolute min and max. It just means that we can't be sure. Okay, it kind of puts us in a place where we're not sure if there is a minimum or a maximum. Okay, the EVT just is a way to tell us whether there absolutely is or absolutely isn't one. Okay, so we want to make sure of two things. We're going to be looking at that worksheet from Unit 3 to see if there's any discontinuities. And we're also going to look at to make sure that the interval that we're considering is closed. It should have only brackets, no parentheses. Now, after that, we're going to start looking for our candidates. Now, remember, as I told you guys, there's two candidates. There's endpoints and there's relative extrema. So first of all, how do we find our relative extrema? Well, last class, we learned how to find relative extrema. What you do is you look for critical values. Critical values are where either the derivative equals 0 or where the derivative is undefined. So we're going to find all those places where the derivative is undefined and where it's 0. These are places where maybe we have a relative extrema. If there's a relative extrema on this graph, it has to happen at one of these places. Okay? Now, it may come about that there is no place where the derivative is 0, or it may come about that there's no place where the derivative is undefined. In that case, we would just say, okay, fine, there's no relative extrema. Or we may find that there's places where the derivative is 0 is undefined, but it turns out those are not relative extrema either. But it doesn't matter. The point is we want to look for candidates, possibilities. And the possibilities of where the relative extrema are is where the derivative equals 0 and where it's undefined. So we're going to have to find the derivative of our function, and we're going to set it equal to 0, and we're also going to find, are there any places where it's undefined? And once again, that's where that worksheet from Unit 3 is going to come in handy. The next thing that we're going to do is we're going to plug in all the values of C that we found in steps 1 and 2 there. We're also going to plug in the endpoints, because remember, not only are, this should actually, I'm pretty sure this should say steps 2 and 3. Let's fix this. So we're going to plug in all these x values that we found in steps 2 and 3, and that's going to give us some y values. We're also going to plug in the endpoints that they give us on our interval to find out what those y values are. Once you're done, you're going to look at all the y values, and whichever y value is the biggest y value, that would have to be your absolute max. And whichever y value is your lowest y value, that would have to be your absolute min. So that's how we do the candidates test. Make sure that there are some extrema first. Find the relative extrema by finding the critical values. Plug those critical values and the endpoints in and see which one gives you the biggest and the lowest y values. So let's go ahead and see, why do we care about this? Why are we obsessing so much over these past few lessons about how do you find the maxes and min? Well, in real life, this is where one of the places where calculus is very useful. A lot of times we want to find where we can find the greatest or the least. Here's a nice little word problem here that would be solved using the whole process that we're talking about now. Suppose you're given manufacturing. You need to make a cylindrical can that can hold 1.5 liters of liquid, and for the purposes of saving money, you want to use as little material as possible. To do this, you want to make sure that the shape of that can, its dimensions, are such that you don't use very much material, but you can still hold the same amount of liquid. And that would be a minimizing problem. And that's where, once again, calculus would come in very handy for doing that. You would be looking for an absolute min or an absolute max. So that's why we care about doing this kind of stuff. But let's go ahead and get into the nitty-gritty here and do a problem. So let's pretend that this graph is not there at the moment, because today we're not going to be doing what we did last time. Last time we found our extreme values by actually looking at a graph, which is not too hard. You just have to know what they look like. But today we're going to do it without graphs. We're going to be doing it by looking at equations. Now some of you guys might be thinking, well, I'm just going to graph it, Mr. Bailey, and I'm going to look at the graph. I mean, why am I going to go through all the stuff you're about ready to show me? Well, because on our test, you have to actually show this work of how you do it. You have to show that you know how to do the candidates test. And technically, you're not supposed to use calculators on certain problems either. So we want to make sure you know how to do it. But I definitely don't mind if you use a calculator to check your work to see if it makes sense. But definitely got to make sure you know how to show all these steps. Okay? All right, so here we go. The first thing we want to do is we want to make sure that the EVT actually applies. Okay, so for the EVT to apply, the function has to be continuous and it has to have a closed interval. Now, it has a closed interval. That's pretty easy to see. That's right here, right? The interval, it has brackets on the left side and on the right side. So that alone is an indicator that, yes, we're dealing with a closed one. So I'm going to put a check next to that. We're good. It's a closed interval. But is it continuous? Well, to answer that, we need to go back to that little worksheet that we had way back in Unit 3 called the Continuity of Common Functions. So there's my function. And what we want to do is we want to look at that worksheet and find out what kind of function we're dealing with. It turns out that the one we're working with right now is a polynomial. And when it comes to polynomials, they're continuous everywhere. They have no discontinuities. So to answer this question here, is it continuous? The answer is yes, because it's a polynomial. Okay, so the EVT applies. And what that means is that for this function, on any interval, there has to be an absolute min and an absolute max. So we now know for sure that yes, there is an absolute min. All right, now that's step one. Now, there's a lot of steps in this process. So if you guys start to feel a little bit overwhelmed, I'm going to encourage you to go back to this slide because I'm just following these steps. I just did step one. I verified that the extreme value theorem does in fact apply. Now I'm going to move on to step two. Find all the values of c for which f prime of c equals 0. So for step two, what I'm going to do is I'm going to find the derivative. So the derivative of this function would be 12x cubed minus 12x squared. Now, I want to find where this function equals 0. So I'm going to solve for x if I set that function equal to 0. Now, how do we solve this? Well, we're going to have to do some kind of factoring. Remember, there's really three main factoring strategies. There's the box method or reverse foiling. There's difference of squares, and there's GCF. And in this case, this one has a GCF. I could factor out a 12x squared, which would leave me with this. And then I'm going to set each one of these factors equal to 0 and solve. Here, if I divide by 12 and then take the square root, I'm going to end up with 0. So there's one critical value. And then if I add 1 on both sides, I get 1. And there's another critical value. So these are some critical values right here. All right? That's step two. Step three. Step three, we're going to look for more critical values. There are also critical values where f prime of c is undefined. But as you guys can see here, f prime of c is a polynomial. So since f prime of c, or sorry, f prime of x, is a polynomial, it has no places where it's undefined. So step 3 does not give me any more critical values. There will be some functions where, yes, step 3 is going to give you a couple more critical values because there may be some places where you have a derivative that's undefined. But f prime of x, 12x cubed minus 12x squared, just like the original function, that's a polynomial. Polynomials don't have any discontinuities. So there's no places where this derivative would be undefined. So let's move on to step 4. Step 4 says plug in all these values of c that were identified in steps 2 and 3, and we're also going to plug in the endpoints. So I'm actually going to do steps 4 and 5 together, and I'm going to, well, I don't know. Yeah, we'll do them together. So steps 4 and 5, I'm just going to do those together. We're going to plug in all the values of c that were identified in steps 2 and 3, and then we're also going to plug in the endpoints. So let's go ahead and do that. Okay, so my endpoints are as follows. I'm going to make a table here. All right. So we had 2 critical values. We had my critical values were what were they? They were 0 and 1, I believe. Now we're going to make a chart here. We're going to plug in our critical values that we got from steps 2 and 3, and we're also going to plug in our endpoints that they gave us at the very beginning. Now, as you do this, my advice is start by plugging in your endpoints first. Okay, so I'm going to put -1 here at the top because it's the smallest, and I'm going to put +2 down here at the bottom because it's the largest. And then you're going to put your critical values in after that. So 0 and 1. It's good to have them in order. And you don't have to do this on your own homework and stuff, but on your notes I would label these. This is an endpoint. And these are critical values. Okay? The endpoints are one of our candidates for where a relative extrema could be, and the critical values are where the relative extrema might be, which is also a place where the absolute extrema might be. So these are our 4 candidates. We have 4 possible locations where the absolute min and the absolute max are. Now remember, absolute mins and absolute maxes are y values. So how do we find the y values? I found all the x places where I found all the values of x where these things could happen, but now I need to actually find what those y values are. How do you do that? Well, you plug it into the original function. Okay, so we're going to find out what f of 1 is. I'm sorry, f of -1 by plugging it into that function. We're going to find out what f of 0 is. We're going to find out what f of +1 is, and we're going to find out what f of 2 is, and then that will tell us all those y values. So these are the possible values. These are our candidates for where the absolute extrema are. And once we actually find out what the y values are, we can actually find out which one is the biggest and which one is the smallest. And we know it has to be one of these because those are the only candidates that can be. And we know that there has to be a max and min because the EVT told us that. So let's begin. Let's plug in -1 first. I'm going to show my work here off on the side. So if I plug -1 into the original function, -1 to the 4th power is +1. -1 to the 3rd power is -1. 3 times 1 is 3. -4 times -1 is +4, which means we have 7. So my first candidate gives me a y value of 7. Let's look at the next one. If you plug in 0, that's kind of easy to see. You're just going to get 0. Let's plug in 1. If you plug in 1, 1 to the 4th power is 1, and 1 times 3 is 3. 1 to the 3rd power is also 1, and 1 times 4 is 4. 3 minus 4 is -1. And then we're going to plug in our last one, which is 2. So let's plug in 2. We have 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. 16 times 3 is going to be 48. 8 times 4 is 32. Subtraction will give me 16. And now, whichever one of these y values is the smallest y value, that is your absolute minimum. Whichever one of these y values is your greatest y value, that's your absolute max. And so we have an absolute minimum here, and we have our absolute max here. $16. All right, so there you have it. That's what we call the candidates test. All right. Now, as you guys know, earlier I had a picture in here. We're not using pictures today, and you can graph this to check your work, but you do need to know how to do all that work that I just did. But let me see if I can bring that picture back really quick. All right, so there's the picture once again. And now, if we're just looking at the graph, it's kind of easy to see where the absolute max is. The absolute max is right here, and then sure enough, that y value is 16. And the absolute min would be right about here, and we could estimate that to be about -1, which is what we found anyway. So we found our absolute mins and maxes using algebra instead of looking at a graph. I'm including the graph just so we can kind of check our work and bring it all back down to earth. But once again, you need to know how to do the algebra to actually get the credit for that problem. Now, here's your steps. So make sure that the absolute min and maxes actually exist using the EVT requirements. Second of all, find some candidates. Some of your candidates are the critical values where the derivative equals 0 and also where it's undefined. Then you're going to plug in those critical values and endpoints and to find the y values, and whichever one gives you the biggest y value is your max, and which one gives you the lowest is your minimum. Okay? All right. So that being said, let's move. I'm going to do another example. Now, this example is not to just do more of the same, but as you guys can see, this problem looks very similar to this problem, but there is a slight difference. Can you guys identify what it is? The only difference is right here. Okay, now let's go ahead and go through our steps and see how that pans out. Okay, so the first thing we want to do is we want to know, does the EVT apply? So, first of all, is it continuous? Well, it's the same function, so yes, it's still a polynomial, so it's still continuous. Do we have a closed interval? And the answer is no. We don't have a closed interval. So EVT does not apply. Now that does not mean that there is no minimum. It just means that we can't be sure if there is a max or a min on that interval somewhere. Okay. Now it doesn't mean that we have to stop there. You can keep going. It just means that in the end, you might realize that all your work was in vain. There is no max or a min. So let's go ahead and go through it. All right, so the second step is to find the derivative, which we already did. The derivative was 12x cubed, right? And then we set that equal to 0 when we solved, and we got two values. We got x equals 0, and we got x equals 1, right? Step 3, we realized that there are none. There are no places where the derivative is undefined. And then we moved on into step 4 and 5, right? Now for steps 4 and 5, we made a little chart. Remember, you always plug in your endpoints first. Your lowest one goes up here. Your highest one goes up here. Then you put your critical values in after that, right? These are all the candidates for where the relative extrema may exist. And then we plugged in our numbers, right? I believe we got 7 here. We got 0 here, we got -1 here, and we got 16 here. And so, but here's where something else different is going to happen. I did everything exactly the same. Even though the EVT did not apply, that just means we can't be sure if there actually will be an absolute min or a max. So that was one difference, was up here in step 1. But in steps 4 and 5 is the other difference if it's not a closed interval. Okay? If it's not a closed interval, then 2 is not included, right? It's got a parenthesis on it. So 2 is actually not a part of the interval. So I'm going to cross that off. Now, the lowest number is -1. So that's my absolute min. This was supposed to be my absolute max. But the problem was, since that point doesn't exist, that means the absolute max doesn't exist either. Okay, now some of you guys might think, well, wait a minute, Mr. Bailey, why can't it just be this one here? That's the next biggest one, right? Well, you got to think about that a little bit more. Let's go back to this graph here on the previous slide. By not including 2 in the interval, let me make that an open dot instead. So let's imagine this being an open dot instead of a closed dot. Well, the next highest candidate was 7, right? And that's right here. But there are points that are higher than 7, right? Like this point's higher than 7. So this is like the issue where when you have an open dot, there is no absolute max because there's always a point higher than that as we get closer and closer to that point, but it never really gets there because that point doesn't exist. So even though, yes, 7 was the next highest candidate, it's not going to be the answer because this guy was supposed to be it, but he doesn't exist, and therefore that kills it. So in this case, you would say that there is no absolute max. There's no absolute max. Okay, so if you don't have a closed interval, then that would indicate that there is no absolute max. Or if it's not continuous, that could also ruin the possibility of there being a absolute min or a max as well. All right, so here's one for you guys, and once again, I've got the graph there, but I don't want to have that there yet, so I'm going to get rid of it. We don't want to look at the graph, we want to solve it using the steps. So I want you guys to use these steps here that I gave you guys earlier, right there. I want you guys to do step 1. So go ahead and do step 1 for this problem. Pause the video. When you unpause it, you will see the solution for step 1. All right, so there's the answer for step 1. Step 1 is to see, is there an absolute min and max? Does the extreme value theorem apply to this? Well, since it's a polynomial, it's continuous everywhere, so yes. And it's closed because I've got brackets on both sides. So yes, we know for certain there has to be an absolute minimum and maximum. All right, I'd like you guys to pause the video here, and then I'd like you guys to do step 2. When you unpause the video, you'll see the solution. Okay, step 2 is to find those critical values where the derivative equals 0. So the first thing we do is we find the derivative, which is 6x squared minus 6, set it equal to 0, and then factor it. First thing I did to factor it was I took out a 6, and then this piece here is a difference of squares, so that becomes x plus 1 and x minus 1. Setting those factors equal to 0 and solving gives us our 2 critical values, negative 1 and 1. So these are 2 critical values. These are 2 places where there may be a relative extrema, and those are candidates for the absolute extrema. All right, go ahead and pause the video here and do step 3, and when you unpause it, you'll see the solution. All right, step 3 is to find those places where the derivative is undefined. But once again, the derivative is a polynomial, and polynomials are never undefined. They're continuous everywhere. So there are no places where the derivative is undefined. All right, let's go ahead and move on to step 4 and 5. Pause the video here and do steps 4 and 5. And when you unpause the video, and actually step 6 too, it's the very last thing we need to do. So do steps 4 through 6, and when you're done, you'll see the solution. All right, now you guys might notice something a little odd about my table here for steps 4, 5, and 6. I'm left a number out. Why did I do that? I have my endpoint 0, that goes in first, and then I have my other endpoint 3, that goes in second, and then we put the critical values in between. But the problem is that the only critical value that's actually between 0 and 3 is 1. So I'm going to include that one, but we're not going to include that one. Why not? We only care about this interval. We're only going from 0 to 3. So even though I had a critical value of negative 1, I'm looking for the absolute min and max on this interval. And this point is not on that interval. So that's why I wanted you guys to always start by putting the left endpoint in first and the right endpoint in after that, and then put your critical values in afterwards. By doing that, you'll kind of naturally catch yourself and realize, oh, that critical value doesn't belong, we'll leave it out. Now, you might not have realized that this time around, but now from the future you will. Always start by putting your endpoints in first, and that makes sure that you don't accidentally include critical values that don't belong in the interval. Okay? But anyway, so the only candidates I'm going to look at are 0, 1, and 3, and by plugging them into this original function over here, I get 0, -4, and 36, which means that my absolute minimum value is -4 and my absolute max is 36. All right, let's go ahead and do student practice number 2. Now, just before I begin this one, though, just so you guys know, all of these problems after this, we're just going to kind of do them together as a guided practice every time. And they're all the same 6 steps. It's just that the functions are different, and those will cause some interesting little twists and turns along the way as we do it. But the same 6 steps apply every time. So go ahead and pause the video here and see if you could do step 1. But before you do, I want you guys to recognize something. The fact that this has an x to the 2/3 power, you can think of that as this, which means that we're actually looking at a cube root function. That's going to be important to know when you're doing step 1, okay? So go ahead and pause the video here and do step 1. So here's step 1. We know for certain that the EVT applies because it's continuous everywhere and it's closed. Now, it's closed, that's obvious. We have our brackets. But why is it continuous? Well, we got to go back to our little sheet. As I've told you guys, we have a linear piece here, just 2x, a polynomial. That's good. But this here is a cube root piece. Cube roots, odd roots, things that look like this, for instance, those are also continuous everywhere. So once again, this little worksheet that we have is going to come in handy when it comes to dealing with these various functions. So since both the 2x and this cube part are both continuous everywhere, that means the whole thing is continuous everywhere. And that means that, yes, once again, the EVT applies, and we know for certain there has to be a min and a max. All right, now I want you guys to do step 2. Pause the video here and do step 2, and when you unpause it, you'll see the solution. All right, so here is step 2. Here's the derivative. The derivative of 2x is 2. And the derivative of 3x to the 2/3 is 2x to the -1/3. If you multiply 2/3 times 3, the 3's cancel and leave the 2. And if you subtract 1 from 2/3, you're left with -1/3. Okay? All right. The next thing that we're going to do is we're going to add, I added this to the other side. So I ended up with 2x to the -1/3 equals 2. Then I divide both sides by 2, and I get x to the -1/3 equals 1. The next step is, how do we get rid of that -1/3 power? Well, if you just raise both sides to the -3, that cancels, leaving x. And no matter what power you raise 1 to, you're always going to get 1. So the answer is 1. So we end up with 1 there. So that was a little tricky. You have to know how to do some, pre-calculus algebra stuff to get that one. But there you go. That's your critical value. Step 3. Now, step 3 is interesting. I'm going to do the first part of it for you. This time there actually is a place where it's undefined. The derivative, as we said, was this, right? It's 2 minus 2x to the -1/3. This thing is actually undefined somewhere, and I'll show you. First of all, if you rewrite it like this, that might help. A -1/3 power, that means we do the reciprocal, right? We put that x to the 1/3 underneath in the bottom. Where is this function undefined? What value is x not allowed to equal? Well, as you guys might recall, you're not allowed to have zeros in the denominator. So x cannot equal 0. So that's one new thing for this type of problem. On the last 2 problems that we did, we didn't have to do step 3. There was no place where the derivative was undefined. But because we ended up with a negative exponent here, that makes a denominator, which means that yes, there can be an undefined place. Anytime the denominator is equal to 0, it's undefined. Okay? So actually, to be a little bit more specific for your notes, it might be good to actually do this instead. Show the work a little bit more. We could say that, okay, that means that x to the 1/3 cannot equal 0, right? And then if you raise both sides to the 3rd power, you end up with x can't be 0. So that's one of our other critical values there. Okay, so now we've got 2 critical values. So one of our critical values is where the slope equals 0, which is at 1. The other place where our slope equals 0 is at 0. All right? Not where slope equals 0, but where our slope's undefined, actually. All right, now we're ready for steps 4, 5, and 6. For this, go ahead and pause the video, and when you unpause it, you will see the solution. And I would encourage you guys to try to do 4, 5, and 6 without the use of a calculator, if you can. Just remember what this means. This means this. Okay? When you unpause the video, you'll see the solution. All right, and so here's my results, and I can see, therefore, that the absolute min would be here, and the absolute max would be here. Okay, now I'll work one of these out just so you guys can kind of see the math. So I'll do the one with 8. So if I were to plug in 8, it would look like this. Now, yes, you could do it on your calculator and get the answer, but I want you guys to also know how to do this by hand in case you need to. So 2 times 8 is 16, obviously. And as I told you, this piece here, it might be good to rethink of that as the cube root of 8 being squared. Now, the cube root of 8 is 2. 2 squared is 4. And 3 times 4 is 12, which gives us a final answer there of 4. So that's how you would work that out by hand if you needed to. Now, sometimes you might get a weird number where you can't actually find the cube root, in which case I'd say you can either estimate it or you can just use a calculator. I don't care. But for these ones like this where you can work it out by hand, I would highly encourage you to do that. All right, so here's another one. And I'm just giving you more problems just so you guys can kind of get a broad spectrum of a variety of type of problems. So let's do another one here. So go ahead and pause the video and do step 1, and when you unpause it, you'll see the solution. All right, so this function is continuous everywhere. When you guys look at your sheet here, there's just sine functions in here, and sine functions are continuous everywhere. So once again, we're good. And it's a closed interval. So yes, there has to be an absolute min and max somewhere. All right, go ahead and do step 2. When you unpause the video, you'll see the solution. All right, so here's our trigonometry stuff. First of all, the derivative. Let's start there. So make sure you got your derivative right to begin with. The derivative of this expression would involve the use of the chain rule on this piece. First of all, you would take the derivative. You want to think of it kind of like this, if you will. Sine of x is being squared. So you're going to multiply the 2 to the front, so that's where this 2 comes from, and then you leave the inside, and then you take 1 away from the power, which makes it a power of 1, which you don't really need to write. But then you're going to multiply it by the derivative of the inside, which is cosine. So that's that first piece. The next piece, the 2 is a multiplicative constant, so that just stays there, and the derivative of sine is cosine. So there's your entire derivative. Now we set that equal to 0. And now we're going to factor once again, whatever they have in common. They both have a 2, and they both have a cosine. So I'm going to pull that out, which will leave you with just sine in this spot here. And over here, it'll leave you with 1. So we're left with sine x plus 1 after we take out the 2 cosine x. Then we set both of these pieces equal to 0 and solve. So for the first one, divide by 2. Cosine equals 0 at pi over 2 and 3 pi over 2 if you look at your unit circle. And now technically cosine equals 0 at an infinite number of places, but we only care about this interval from 0 to 2 pi, which is basically just the entire unit circle from 0 all the way around once. So that's kind of convenient. If they gave you a weird interval, you'd have to think a little bit harder about which values to pick. But in this case, pi over 2 and 3 pi over 2 works. As for this side over here, subtracting 1 on both sides, we look for where sine of x equals -1, and that happens at 3 pi over 2. Now, since this answer here is the same as this answer, we don't need to write it twice. It doesn't add any new information to us. So basically, we just end up with 2 critical values from step 2. All right, now step 3, go ahead and pause the video here and see if you guys can find the solution to that. And when you unpause it, you'll see the solution. Well, for step 3 doesn't give us any critical values. There's no places where the derivative is undefined. This is a sine, this is a cosine, and this is a cosine. And when we look at our little sheet up here, both sine and cosine are continuous everywhere. So therefore, this little expression that we're looking at has to be continuous everywhere. Lost my page. So since there's no discontinuities, there's nowhere where the derivative would have or would fail to exist. All right, so we'll move on to steps 4, 5, and 6. And go ahead and pause the video here, and when you unpause it, you'll see the final solution. All right, and there's our answer for steps 4, 5, and 6. We plugged in our critical values, we plugged in our endpoints. The highest value is 3, the lowest value is -1, and that gives us our absolute mins and our absolute maxes. Let's do one more, just to give you some more experience with other types of functions here. Let me go ahead and close out this graph a little bit. All right, so go ahead and pause the video here and do step 1, please. So in this case, the extreme value theorem does not apply. We have a discontinuity at 0, which is on the interval that we care about. Since we're going from -2 to 2, and there's a discontinuity there, then the EVT doesn't apply. And what that means is we can't be sure if there is an absolute min or if there's an absolute max on that interval. Okay, so we can't be sure that there actually is a min or a max at this point in time. Now, why is there a discontinuity? Well, that's a rational function here, and as you guys look at your sheet here, rational functions, the denominator is not allowed to equal 0. You have a discontinuity anytime the denominator equals 0. So x squared can't equal 0, which means that x can't equal 0. So, and x equals 0 is in between these two values, so there you have it. All right, but let's go ahead and just go through the rest of the problem and see what happens anyway. But we are not guaranteed that there is a absolute min or max. There might be, but we just can't be sure. All right, so let's go ahead and see what we can find. So for step 2, we want to find where the derivative equals 0. How do you find the derivative of this? Well, you guys might have thought, okay, well, I'm going to do the quotient rule, low d high minus high d low. It will work, but it's a lot harder. An easier way to find the derivative of this would be to rewrite this as x to the -2 power and just do the power rule, okay? Which gives us -2 over x cubed. Now, that's impossible for this thing to equal 0. A nice little note for you guys, which I would encourage you guys to write down, is the following. We're going to do this a few more times later on, but for a rational function, if you want to find where it equals 0, you set the top equal to 0. Now, for this particular problem, you can't set 2 equal to 0. You can't say that -2 equals 0. That doesn't make sense. So there's no solution. Now, for step 3, though, where we want to find where it's undefined, you set the denominator equal to 0. So in this case, I'm going to say, okay, x cubed equals 0, which means that x equals 0. So I have one critical value. But that also happens to be where the function's discontinuous, okay? So it's not uncommon where that place where my function's discontinuity was, that will be a place where you have a critical value as well. But the problem is that anytime you have a critical value at a discontinuity, you're not going to be able to use it. We can't use that as a candidate. Since f of 0 doesn't exist. We've already established that over here. There was a discontinuity at 0. So anytime you end up with a critical value, which is a place, and that critical value is a place where the function's undefined, we're not going to include it. So when you guys do steps 4, 5, and 6, we're not going to include 0 in the final output. All right. And so here's the final result here. My endpoints are -2 and 2. I only had one critical value. It was 0. And we already know that's not going to be a candidate anymore, so we don't even really need to include it in the table like this. But now I'm confused. What is my min and what is my max? It's kind of difficult to tell. Is 1/4, is that a minimum? Is it a maximum? And by the way, this is just kind of a coincidence. I mean, you could have, if I change the interval, if I change this to a 3, then you'd get a different number here. And I don't want you guys to think that, oh, well, maybe, you know, whichever one's smaller, that would be the min and max. Anytime one of your critical values turns out to be undefined, you got to be really careful. So we might want to make a note of that. Let's go ahead and write that down really quick. So if your critical value is a place where the function's undefined like this, then you really need to kind of look at the graph to come to a conclusion. Let me show you the graph and I'll show you why. So as I'm looking at this graph here, here's my 1/4 on the left, here's my 1/4 on the right. So it turns out that 1/4 is an absolute min. So I can go ahead and write that in there now. And it's there twice. It doesn't really matter how many times that number appears in the table because it's just the lowest number. So the lowest y value doesn't matter how many times it appears. The lowest y value is 1/4. That's the bottom point of the graph. But let me erase this ink. It's kind of getting in the way of my thought process. So 1/4 is the absolute minimum on this graph, but as you guys can see by the graph, there is no absolute max. So you can tell by looking at the graph. Now technically, you guys could do a limit. Now I'm not going to ask you guys to do that in this class. It's just a little bit, it's just, I've never seen the question even asked. It could happen. But technically, you guys could find the limit of this function as x approaches 0, since that's the place where it's undefined. Now if you actually get a number, that's interesting, but in this case, if you found the limit from the left and the right, what you're going to find is it would be infinity on both sides, whether you're going from the right or the left. And what that means is that there's no absolute max. It never stops going up. Now, I'm not going to ask you guys to do the limit stuff. I would say just go ahead and take a look at the graph, and you can kind of tell, oh, well, there's no limit there. It doesn't really seem to exist. There is no absolute max. Okay, so we saw two situations where you can't include numbers now. One of the situations we saw was here, where the critical value doesn't exist. And in that case, really, you just kind of need to look at the graph. The other one that we saw earlier today was this one where you have a non-closed interval. For those ones, you don't really need to look at the graph. You just need to handle it the way that we handled it earlier, which was by go ahead and just do the process, and if that endpoint turns out to be your max, but it's not included, just know that there is no max. But anyway, that's as many examples as I think we'll go through today, and we'll call it quits, and we'll see you guys next time.